Okay, so today we'll look at how to generate the various timing signals inside an SRAM. And this is again kind of one of those few places where circuits, you have to kind of work at the circuit level as opposed to at a much higher level of behavioral HDL like Verilog or VHDL. So let's again review the basic timing which we need for an SRAM. So here what we have is we are talking of synchronous SRAMs. So the accesses are triggered by the clock. So there is a clock edge which starts the whole access for the SRAM. After some time the word line gets activated to turn on the access transistors for the cell. And also if you recall, the memory cell is connected to the bit lines which are pre-charged to a high value. So before you turn, or around the time you turn on the memory cell so that the access transistors start discharging the bit line, you want to disable the pull-up. Whatever is holding the bit line to VDD, you want to disconnect it so that the bit lines become floating, or at least they are not kind of held high. Otherwise the memory cell will not be able to basically pull down the bit line. So that is what is done here. Remember the pre-charged transistors are PMOS transistors because you want to pre-charge the node to VDD. So to shut off the PMOS, the pre-charge voltage goes from 0 to 1. And then the bit lines start discharging, and after some time the sense-amp enable kicks in to turn on the sensing. Okay, so this is basically, these are the signals the basic signals which we need to generate for your SRAM to work. So what you have here is some kind of a timing generation block. So what is shown here is a row decoder. So I'm kind of showing a piece of the memory. So there is a row decoder out here which takes the address and certain other signals like read, enable, select, etc. and decodes and activates a particular row. Okay, now in addition you have, so this is the array out here, array of memory cells. So what I've shown out here, and these are the vertical bit lines, what I've shown here is the pre-charge circuitry. If you recall, the pre-charge circuitry was essentially two PMOSs pulling each bit line to VDD and then one PMOS shorting the two bit lines. So there are three PMOSs. And then you have the sense amp, which usually now is basically a clocked sense amplifier. You have two back-to-back connected inverters with a transistor at the ground which is turned on or off. So that is the sense signal. So these signals go like this, and in addition you might have a signal to disable the word line. I've kind of shown it like this. So you have a basic timing generation block. So the question is what is this inside this block? What goes in? What are the considerations, etc. Right? Now before we do that, let's just understand a few parameters related to timing for the SRAM. First is, the SRAM, you give an address and the control bits, read, write, etc. and these are synchronous with respect to the clock edge. So just like in any pipeline system, the previous circuitry generates the address and says, okay, give me the data corresponding to this address, and the address has to come in and be ready, has to be set up before the clock edge. So that is the standard setup time requirement which is there. Once the edge captures this address, the SRAM does its thing inside and then gives the data out. After some time the data comes out on the output port of the SRAM. This time is called the access time. Time required to access a piece of data item inside the memory. After some time you can repeat this operation again, and the period of repetition is the cycle time. What is the fastest period of repetition? Okay. So it is not necessary that access time and cycle time be the same. They can be different. You could have situations where cycle time is more than the access time. Okay, you can access, you give the address, the data comes out, but before you can give the next address you have to wait for some time because there are certain internal states which you need to reset and so on, and so it takes time, and then it's ready to take the next access. Similarly, you can have cycle time less than the access time, where you can keep giving new addresses before the data corresponding to the old address has come. That is nothing but pipelining. Right? In pipelining, you essentially you pipeline a logic block, and the output of that comes after some number of cycles, but you can keep giving new inputs to that pipeline logic block. Can you repeat the question? That is right. So when we pipeline the SRAM, again internally, you could have the SRAM broken up into, say, usually you might have like two-stage pipeline. So internally you might have to insert one more pipe stage, which is triggered by this clock. So that could be one way. But if you see in a SRAM, what happens? If you go, let's go back to the thing. Here you have some number of address bits, and these address bits get decoded into one of many word lines. So now if you see, where would you put in the pipe stage, and then you have the data coming out. So typically the time to decode and activate a word line, and from the time the word line goes ahead to the data coming out, are roughly equal. Okay, 40, 60, I mean, there's a little bit of variation. So if you have to put a pipe stage, it has to be somewhere out here after the decoder. But then you might have like 8 bits of data, or 8 bits of address, or maybe 10 bits of address, or even 20 bits of address for a megabit. But then you see the number of the output of the decoder is just an exponential growth in the output of the decoder. So if you put a pipe stage after the decoder, the number of flops required just goes up exponentially, and you have to send clock to all those. So power goes up. So a straightforward way, just saying what I do for logic, I put the flop and have my pipelining done, that is not a good approach, because area and power become enormous. So how do then people do pipelining? How do people pipeline the memories? Well, you use what is called pulsed techniques. We'll see that probably in the next class, where there is no pipe stage, but internally you have pulses which are flowing through. So you can have multiple pulses in transit. And it's kind of similar to another concept called wave pipelining, where again it's kind of like, imagine you have a transmission line or a fiber optic cable where you have a long wire, and the latency of the wire could be nanoseconds, microseconds, etc. But you can send information at a much faster rate. The bits can be very small because the bits are all in transit. So it is kind of like a wave, bits are flowing. So similarly, there is another way of doing pipelining called wave pipelining. So where you don't necessarily have sequencing elements or flop elements, but data items or data tokens are in transit, and multiple data tokens are available. Now it turns out with wave pipelining, there are certain very stringent conditions that need to be preserved. There has to be a lot of symmetry and so on, and so typically you don't use wave pipelining for general logic, but it works well for memories because there's a lot of symmetry. But for example, from the decoder to the decoder output, it's kind of essentially symmetric. So we have setup time, we have the access time, and we have the cycle time. And typically you are interested in reducing all of these because you want fast access. One of the things is, speed of course is good from a performance perspective, but also you can trade off speed with power. So if you have a design which your friend has done a design which is faster than your design, then that person can leverage that by reducing the voltage, for example, and slowing it down to meet your speed and hence consuming less power. So you can trade off speed and power, as we discussed when we are looking at power optimization. Now let us look at this access time, which is the time for the data bit to come out of the memory. What are all the different components? So once you set up the address with respect to the clock edge, the first thing which happens is the decoding. So the address gets decoded and the word line corresponding to a particular row gets activated. So that time you can say T decoder, TDEC. After the decoding and after the word line goes high, the bit bar are, depending on the data, either bit or bit bar starts discharging. Both don't discharge, one or the other discharges, the other remains at VDD. And after some time, a sufficient voltage is developed on the bit line pair. So you need a certain minimum voltage for the SRAM to properly detect that reliably all the time. So let us say delta V min. So you need some time for the bit line to split and have at least that much voltage. Typically, you see these voltages, as I said, are kind of small, maybe about 100 millivolts. So you can model the memory cell as a current source for that duration. So the cells will have a certain current. When you turn on the word line, the zero side of the memory cell starts pulling down that bit line. So it's pretty much like a current source because all the transistors are in saturation. At least the transistor which determines the current is in saturation. So bit line time is essentially the capacitance C delta V by I. That is bit line time. C is the capacitance of the bit line. Delta V is the voltage you need. Delta, in this case, delta V min is what I've called. And the current is the current of the cell. So that is the amount of time required to generate that voltage delta V. And once the bit line split, you also turn on the sense amp. Okay, there might be a small delay. Maybe, there is an ideal time you want to turn on the sense amp, but what you have generated is a little bit extra. So I just call it T sense amp overhead. And then the sense amp does its job, amplifies, and then you drive out the signal. So that is the time to D out. That's what I call here. So the overall access time is sum of all these components out here. Now we'll look at we'll look at the decoder in the next class, not in this class. What you can do to reduce the decoder delay. Decoder is a completely combinational logic. I mean, it's basically a regular CMOS logic, and we have already seen techniques for reducing delay for logic gates, right? Essentially, you size things so that you have minimum delay is when you have equal efforts and so on. Now, in addition, you can do some some more things beyond that, and we'll discuss that when we discuss about the decoder. We'll here focus on now as far as the bit line T bit line goes. What you can do is the cell itself, as I said, the cell current, the delay is CV by C delta V by. Delta V is kind of defined by the offsets of your sense amp. So it's kind of hard to get below a certain value because, again, as I said, you have so many of sense amps, and across process voltage, temperature, you need to have good yields, and so maybe 50 millivolts you can really push it down. But that's about it. Cell current, if you make the cell bigger, because transistors will be bigger, you'll have larger current, so delay will come down. But again, it's not a good idea because it's more important from a system level to have more memory rather than fewer memory cells with larger size. So you are only left with the option of capacitance. And capacitance you can reduce by basically architecting. Maybe you, instead of having a 128 rows where the bit line column runs across 128 rows, you might say, look, I'll go for 64 rows, or maybe I'll go for 16 rows, come down all the way. So that becomes more of a architectural study because every time you reduce the size of the bit line column, you have to introduce some extra circuitry which leads to the overall area. So you have to kind of do that analysis. Finally, this sense amp overhead, sense amp enable overhead is something which you can try to reduce, where magically somehow you perfectly generate the sense amp exactly at the right time. Okay, so we'll just look at in the next few slides how to do that, and then sense amp to data out. That is again what you have studied before. There is nothing new out there in terms of optimizations needed to speed it up. There is a certain load the memory has to drive. Sense amp output is pretty much digital, and it has a certain drive strength. So you have to buffer it up and drive. There's not much you can do there. So these are the components which determine the access time. What about the cycle time? Like, why is cycle time not the same as access time? Well, one of the big reasons is basically got to do with the precharge. So let us look at the condition. Typically what limits the cycle time is read after a write. That means you do a write in a particular row, but then you read maybe from a different row. But both these accesses use the same bit lines, right? The bit lines are shared. There's a single bit line in which you either pump data into the cell or you read data from the cell. So it's a shared resource. So how quickly can you turn around the bit line? Really, that's basically what limits it, because the bit lines usually will be large, a lot of capacitance. Because when you do a write, so the write enable bar is 0, so I'm doing a write. So after some time the precharge and the word line go high, so the bit lines are no longer held high, but then I'm not shown out here, but something which is driving data onto the bit lines. There's a driver which we said essentially it's just two NMOSes which drive the either bit or bit bar down depending on the data value. Data is 1, bit bar is driven down to ground, data is 0, bit is driven down to ground, so that you put in the right polarity of data into the cell. Here there is a small error here. This bit bar discharging should happen after the precharge has gone high, because precharge goes high means it will disable the PMOS. If I start writing into the memory cell while the precharge is still low, that means PMOS is also holding it to VDD and the right driver is also trying to drive it down, so there will be a lot of current. So this should be pushed to the right a little bit. Anyway, after finishing, when I do a write, the bit line is always a full swing. The bit lines are always pulled all the way to ground, I mean one of the bit line pair. So when you finish the write, and you can only finish after the word line is low, is when you start pre-charging back the bit line, and it has to be ready by the time the next word line goes high. Remember what I said, that suppose the next time when you're reading a memory cell, the row from which you're reading has this value which is opposite to this value. So this value say had bit 0 and bit bar 1. So as it's pre-charging, it better pre-charge and equalize the two bit lines, because any residual voltage difference will eat into your voltage margin, because the memory cell has to overcome that and turn the bit, and get me the voltage of the opposite polarity. So the time required to do this kind of usually limits the cycle time, because these are large capacitances, and again you can't have very large size pre-charge transistors, etc., because everything is kind of constrained area. So that kind of limits the cycle time. So now let's look at one simple way of doing this timing generation, right? Let's look at the read timing generation. Usually writes are much simpler, because in a write, you're done basically out here. You generate, you put the data, and after some time you give enough, whatever you did for the reads will also work for the writes, as far as making sure the writes work. In the reads, the tricky thing is generating these, especially the SRAM signal. So what happens is that, so one simple way of doing this is to basically say, that you're going to use the clock edges. You have a rising edge which starts the access, and then you use the falling edge. You break it up into two phases. In the phase when clock is high, you do something, you decode, etc., and get the data to the input of the SRAM. And when in the second phase, you activate the SRAM and get the data out. So that is one way in which you can do, where now again you can use basically implementing this turns out to be quite straightforward, and this works. So this works well. It's quite robust. Why is it robust? Because say there is a problem that maybe your timing generation was messed up. Basically what you want is that the SRAM enabled signal should not come too soon, because if it comes too soon, there is a danger that the voltage is not enough for it to pick it up properly. If it comes late, functionally it is okay, but you're losing timing, you're wasting time. So that is the thing. So with something like this scheme, what you have is, you have two edges. The rising edge does something, falling edge does the other thing. So by controlling the spacing of the rising and falling, you can separate out the two. Controlling rising spacing of the two could be basically by slowing down the clock. You slow down the clock, and if you keep the same duty cycle, that is percentage of time clock is high, low, everything scales out, and so you can get it to work. So it's a kind of a safe, robust approach, but it's not very efficient from energy and speed perspective, and so you can do that for it works, but if you want to really push speeds and reduce energy some more, you have to do something more.
So we can have enable only after we've pre-charged, right?
Which enable?
The sense enable after we can read only after it's pre-charged.
So the question is, what is the relationship between the timing of pre-charge and sense enable? And here again I've been a little sloppy in this notation. The thing is that, see, I mean, in this sketch out here, yes, you don't want the pre-charge to come before the sense amp enable goes high. Because if the pre-charge comes before the sense amp enable goes high, you will wipe out the data. You worked hard to set up a small data difference. And then before the sense amp picks it up, you turn on the pre-charge. That is not good. So you want to interlock. So what is called interlocking. So some of these signals you want to, for example, you want to ensure this kind of ordering. Pre-charge is released, then you turn on word line, then sense amp enable goes high, and then pre-charge comes down. So there is a certain relationship which you have to maintain between the signals. Okay, so that you can do by your circuit implementation. So ensuring that you always have, the pull down happens when after sense amp goes high, that signal is used to gate and turn on the pre-charge. So that way it will ensure that pre-charge doesn't turn on before sense amp enable goes high. So that is basically called locking. You interlock by that way. So the other thing is that once the sense amp enable fires, there is no reason to keep the word line on anymore. Because if you keep the word line on some more, what will happen is the bit line will keep on discharging. Again, you are losing energy because your job is done. So just shut it off, right? So that is basically. So there are two things out here: shutting off the word line and turning off the sense amp, and they are kind of related to each other because they are related by the delta V. If once you have generated the right delta V, you turn on sense amp, shut off the word line. So this sense amp overhead, you want to make sure it's at least positive. It's never less than 0, and if possible as close to 0 as possible. This overhead is the time beyond this delta V min, beyond the time which it took to generate delta V min.
This is depending on the delta V, right?
Delta V, yes. So what happens is usually delta V min, as I'm saying out here, is delta V is kind of determined by the sense amp offset. We'll kind of look at that. What is sense amp offset? So you need to be able to generate a voltage difference overcoming all offsets. There might be a residual offset due to your previous pre-charge, maybe there is a few millivolts there, sense amp themselves contribute a few millivolts, certain other asymmetries. So you have to do an accounting and say, look, I want at least 100 millivolts to be generated, such that across all conditions my sense amp will fire and will properly sense and give me the data value. So if you look at the sense amp, let's come back and look at the sense amp again and see why you have these offsets, right? So our sense amp is essentially two inverters connected back to back, just like the memory cell. But in addition, the ground, instead of connecting directly to ground, it's going through this extra transistor. When you turn on the sense amp enable, when the sense amp enable is low, both these nodes are connected to bit and bit bar. So they are pre-charged to high. And then one of them goes down by delta V. But they are still close to VDD. So this node voltage is also close to VDD minus VT, right? Because if this is VDD, then you have a threshold drop out here. So this is VDD minus VT. So when sense amp enable goes high, it turns on this transistor which discharges this node. It pulls down this node. And as it starts pulling down this node, both the transistors start turning on, but one of them gets turned on faster than the other because of the initial voltage difference, and so that helps to drive the sensing. For example, so for now let's just ignore this delta VTH offset voltage. If let us say on the left side the voltage remains at VDD, but the right side the voltage goes down by a delta V, maybe 700 millivolts. So when you turn on the sense amp enable signal, as you start pulling this node down, see the right side voltage is connected out here. So the right side voltage goes to the left side NMOS transistor and it is lower. So this transistor is not able to, if everything was, and the current through it will be always less than the current through this, because this guy's gate voltage is higher, plus, whereas this guy's gate voltage is minus. So this larger current will also help to pull down this minus even more. and so it's in the same direction, and so it's a positive feedback, and you get the right data value. The problem comes when there is some offsets due to various reasons. We'll just see that, where even though this had a lesser voltage and you would expected this transistor to be having smaller current, but actually what happens is that this transistor has more current than this transistor, even though it has smaller gate voltage. This has more current than this guy. It could be because essentially due to various reasons the threshold voltages are not the same. So one of them has a larger threshold. That means, say this guy has a larger threshold voltage, or this guy has a smaller threshold voltage compared to this. So because of that, what you have is, so here if I had shown the polarity opposite, it would have illustrated better. But basically you have the, even though you created this external voltage difference, it is no longer sufficient to create a corresponding current difference, because internally the threshold voltages are still in the favoring the other transistor. So what you have is, as we said in one of the earlier lectures, all the design parameters are basically random variables: width, length, threshold voltage, substrate doping, etc., etc. And because of that, you'll have always a mismatch. Two transistors will never match perfectly, so you'll have some mismatch, and that mismatch, there is a systematic component, there is a random component. Systematic component is a component means you can predict what the mismatch is, and you can take effect, you can kind of do corresponding things to reduce that. For example, if you have, say, this transistor on the left side laid out like this, that means red is the gate and green is the diffusion region, so current is going horizontally. And say the other transistor you lay it out like this, that means the gate is, the transistor is lying on the side, so the current is flowing vertically. So they will not match well. Okay, the current directions have to be the same. I mean, you need to have the transistors laid out. The poly, everything has to be in the same direction. Orientation has to be the same.
Why, sir?
Because of the way, what happens is that the processing, when they expose it, when they do processing, they expose it to radiation and, particles and so on, which do etching and implantation and so on. So there will be a certain tilt, right, which will be happening. So that small tilt, if it's coming, it will have a different impact on this and this. Okay. Similarly, current direction has to be the same. So the transistors are not symmetric, even though we show source and drain, and we think it's, the behavior of the transistor is the same in both ways in schematic, but in reality they will have a slight difference. Remember, these are all very small differences. Typical digital logic, you will not notice any of these issues. But when you are talking of these very small voltages, you need to start paying attention to these. So when you lay out these, you have to point all be in the same orientation. Similarly, if you recall now, the memory cell, the flat layout, all the transistors are in the same horizontal orientation. Here in addition, you could try to make the current directions the same, but it turns out the layout kind of becomes messier. But if you were to do very sensitive analog circuits, you could try to do that. And there are certain other things also you could do to improve the matching. But essentially you do all of that and then you end up with still about 50 millivolts, because you still have the random mismatch. The only way to deal with random mismatch is averaging. If you have uncorrelated variations, if you do averaging, the standard deviation goes down. Increasing the size of the transistor is like averaging. It's like putting many little transistors in parallel. Okay, each one has a small variation, but you have so many in parallel that the standard deviation goes down by the square root of the number of things in parallel. Right? That is basically the idea of increasing the size, but you have a certain size constraint. You can't make it too big. Within that size constraint, you have to try to get as good a layout as possible. So you end up with some offset. You need to generate a certain minimum bitline differential, which can be reliably sensed.
So actually on the orientation of these transistors, whether the variation of voltages is totally randomness, or we can prejudge that one of the orientation is having higher or other is lower?
Yes, so that is a good question. This is actually a systematic variation. You can predict, but you need to be able to go all the way to the processing. and be able to understand how the processing is happening and so on. So then you can predict. So it's kind of like saying when you do a coin toss, if you knew the complete physical situation, and then can you and if you believe that classical mechanics controlled the way the coin flipped, and if you knew the dynamics of every molecule and everything you take into account, you will be able to predict, right, how the coin will flip and keep. But that amount of information, if you don't have, then you basically say you'll model it as a random process. Of course, with quantum physics, you basically you cannot really predict, because inherently nature is random. So similarly out here, that is why these are called systematic variations, where you can account for these variations if you can study all the factors which go in and determine that. So these deterministic or systematic variations can be controlled or can be overcome by doing specific things either in the design or in the design, and that is done also a lot of times. So whereas these random ones, you really you just have to do averaging if they are. That's the only way to deal with these random variations. So how do we now generate the SRAM timing? So basically what you do is I just want to introduce this concept of self timing. Okay, it's a very interesting concept where internal timing, there could be other applications where you have to generate multiple timing signals, and then internally you generate these signals locally. You don't rely on a clock, but internally you are somehow generating these various edges. So this is one particular application where what is also being done is the timing is being generated using a replica of the memory cell also, because you also want to generate a timing such that you make the required voltage develop. That voltage is determined by the cell current of the memory cell. So somehow you need to kind of incorporate that. How do you know you want to generate a timing such that you have that much voltage developed on the bit line, but then that is determined by the memory cell. And the memory cell, as we discussed in the last lecture and the before, they are done by the foundry. It's very custom designed and so on, and they might even violate some of the design rules only in those places. So it's very hard to mimic it with just logic gates. So it's better to use a copy of a memory cell in your path. So basically what is done here is that you generate, you decode, and then you generate you have a row decoder which generates the row, what is called a global word line, and then for a particular block of memory, you say, okay, this is the block I want to activate, and this vertical line block cell goes by, and then that generates the local word line. Now in addition, what you have to do is you basically turn on a replica memory cell. Okay, there is a main memory cell, there is a replica cell. It's the same as that, but it's always hardwired to have the value of 0. It's hardwired. And the replica cell discharges, and that triggers the SRAM as well as that triggers the shutting off of the word line. So there's a little loop there. So a lot of these self-timed circuits will have some loops because you want to locally generate pulses. And in this loop, the loop timing is basically determined largely by the replica cell pulling on the replica bit line. Of course, now you can ask the question, the memory cell is so weak, and this bit line, it takes a long time for it to generate a full logic swing. So that is why we have a SRAM, so that even when the swing is small, we activate the SRAM. What about the replica? Doesn't the same apply there? Then what we need a SRAM for that? Then how do we activate that SRAM? So it's a never-ending problem, right? So to deal with that, what is done is basically for the replica, you do away with the SRAM, but you have a simple inverter. But then the replica bit line voltage should be a full swing. So you still want to have the tracking. So for example, if you have a full swing supply voltage of 1 volt and you need a 100 millivolt swing, then what you can do is the replica bit line capacitance you reduce by a factor of 10. So in the same time it takes to get 100 millivolts in a capacitance C, in that time you would generate 1 volt in a capacitance C by 10. So that is kind of the idea. The currents are kept the same by using the same cell, but the capacitance you play around to reduce to generate full swing, which can be detected by a unclocked sense amp, which is just a simple inverter. So you turn on, you have this feedback word line which generates the feedback, and then you activate the sense amp. So one important thing here is that you're basically using some physical entity which you want to kind of predict. The same, a copy of that is being used. Okay, so that tracking is better.
You can do larger area.
Yes, you need to put in one extra column of the replica cell.
For every column you have to do.
Not every column, one per array, or you can have some interspersed between the arrays. So each one will control a group of columns. You just need one. You don't duplicate, but you have extra one for the entire set of columns.
We can reduce the size of this main only for purpose. Instead of replica using just a copy of replica instead of main this root column.
The problem is here we need to know and set the replica to always discharge. So the data is fixed. I can't use it for storing information. It is only used for generating timing.
So I can be multiple delay stages there.
This is just buffering. See, because you have, that is another thing, because you generate the signal and you have to buffer and drive so many sense amps. So you'll naturally have some buffering required. So this,
Intended for optimizing the delay.
since you have to have buffering, but now you need to, of course, control the sizing of these and optimize the delay. We'll look at that next, right? But before that, just to kind of illustrate this, basically you have the feedback word line which generates a timing signal, replica bit line, after some time delay of y. Okay, and then that signal goes and shuts off the feedback word line, FWL, after some delay. So if you have a delay of x from FWL to the word line, then the overall delay from rising edge to the falling edge of the word line is x plus y plus delta, because you have y plus delta plus x coming here. Okay, that is when this word line falls. Now if you look at when the sense amp enable goes high, after this falls, if you can ensure that from feed FWL to sense amp rising is also x, the rising time of sense amp enable is again x plus y plus delta. So both are happening around the same time. So what is required is the matching of the delay from FWL to word line to this guy. So these have to be matched. Okay, so these two paths have to be matched. And when you want to match delay chains, right? So one thing again you have to remember is that in a delay chain you have rising, falling happening, alternating. Rising is determined by the PMOS, falling is determined by the NMOS. It's always better to match PMOS to PMOS, NMOS to NMOS. Because you can have process skews where, the PMOS and NMOSes and NMOSes are correlated much more than NMOSes and PMOSes. So try to match like to like. So here what you have to do is, if you can match the sum of delays of falling to sum of delays of falling on the other chain, right? And similarly sum of delays of rising to sum of delays of rising in the other chain, then you will have a reasonably good match across different process conditions. So the two things what we are saying here is, try to use a replica of whatever you are doing. See, this replica, concept of replica is used in many places in many different situations. For example, in analog circuits, when you want to bias something, you have a main circuit and you want to bias it, you take a copy of itself, you just set up the connection so that it generates the bias voltage. So the replica and the whatever you want to do track well, because it's the same circuit topology, probably even the same layout, everything is same, so they match well. So the second thing is, try to match PMOS to PMOS, NMOS to NMOS. Trying to match NMOS to PMOS is it can lead to a lot of issues. You need to have additional compensation for that. So again, to answer the question earlier, so what you will have is, you have a memory block. One thing which is done in these memories is that usually you will have sacrificial layers, sacrificial rows and columns. So on the top, bottom, left, right. So those cells, the property of the memory cell, as I said, because the cells are tiny, they really are exposed to a lot of variation. The neighborhood of the cell, the neighborhood layout has an impact on the transistor characteristics. So if you want extreme matching, even coming back to these, really, so even though you have these two transistors laid out and everything current is the same, if you still might have to do additional things if you're really paranoid about matching, to look at the neighborhood. What I see should be the same as what my matching transistor sees. Then you'll have even better matching. And that is because the neighborhood has an influence on how the ions go in when you're doping, how the stresses are, and so on. Because these modern processes, stress is used to change the mobility. So depending on the physical structure around you, the stress could be a little different. And so the mobilities will be different. And so the transistor drive currents could be different. So you have it.
You just tell in the earlier slide, you just tell matching PMOS and NMOS.
What
is the concept?
See, the concept is that, you want to match, let us look at the delay out here. The delay, we want to match these two delays, FWL to word line rising and RBL to sense rising. It consists of this falling, this rising, this falling, this rising, right? When this rises, the output of B1 falls, output of B2 rises, output of B3 falls, output of B4 rises. That delay has to match to this situation where output of S1 rises, output of S2 falls, S3 rises, S4 falls, S5 rises. So now you have two things you want to match. See, this problem also happens when you want to generate clock and clock bar. Okay, you have a single polarity signal and you want to generate a differential signal. Okay, and you want the differential signal to have to happen at the same time, so that there is difference. But then one path will have even number of stages, the other path will have odd number of stages. So you need to match those two. Right? If they have the same number of stages, it's a trivial problem. You just replicate it. But when there is different number of stages, what do? You have to go in and look at this, where you say, look, I'm going to have, for me to generate a signal, I have 2 rises and 2 falls, whereas here I have 3 rises and 2 falls. So you try to match the falls to falls, the sums, and rises to rises. Now, how do you do the matching? This you have already, you know how to calculate the delay. Basically, sizing, you have to adjust the sizing, you know the load, etc. So you can kind of use the basic logical effort equations or delay equations and try to set up these equations and come up with the size values. Of course, the equations are always approximation, but so they'll give you the starting value, and then you have to optimize further by fine-tuning it. So what are we trying to do out here? Here what we are trying to do is the replica cell is supposed to mimic a memory cell. But in a memory block, you have so many memory cells. So which one is it mimicking? So you have all kinds of, you have a complete spread. So if I just use a single cell, and the single replica cell will also have its own spread. So as you are scaling down, you need to actually now increase. Essentially, you need to predict the mean. You can only you can kind of try to hit the mean of the current, cell currents. And to get to the mean, you have to do a lot of averaging. So what you can do is, you can use multiple replica cells. So that is something which people are doing now, where instead of a single replica cell, use multiple replica cells. So you turn on all of them at the same time. So all the cell currents add up. Remember I said you reduce to get me this large swing with the same delay, I reduce the capacitance. Instead of that, you increase the number of cells so that you still get the same effect and you get averaging. So yes, so you can have a column dedicated, or maybe you can even have a row done. So depending on the architecture, yes. Any other questions?
Sir, will you explain the purpose of replica cell?
So the question is, explain the purpose of the replica cell. So basically what we have to do is we have to somehow generate this time window. I'll call it TWL width, which is a window over which the memory cell is turned on and it generates the required voltage. I need to have a measure of that time. How much time does it take for my memory to generate my minimum voltage which can be detected by the sensor. So that is the timing generation I need to do. So you can kind of do simulations and see how much it takes, and somehow in the chip you try to put in that delay generator which will generate that. Now the thing is that see, whatever solutions you have should be, it should be kind of simple enough to get the job done, but not so simple that it really doesn't do it well. And also it cannot be, see, on the one hand, for example, you can say, look, I can have maybe some precision control delay line, okay, where I'll know exactly in picoseconds, absolute time units I can get. Maybe I'll put that in and then generate these edges. But then the complexity and area overhead becomes very large. So you need to have a way by which you can kind of get the solution to your problem. And here one of the things is that the actual delay you need really depends on the memory cell and the process shifts. You cannot say it is so many nanoseconds because it is, a different chip will have a different delay. So you need to have circuitry which tracks the actual conditions of that chip. So whenever you have to do that, you need to use a replica circuit which will essentially sample the same process condition as the main circuit.
But I can fetch it from my original memory cell only. Why do you need replica?
Because in the case of the replica, you have to always discharge the replica bit. In the original memory circuit, there is bit or bit bar. Either of them can go. Right. Second thing is the replica, sensing the replica bit line, I cannot use a standard clocked sensor, because if I use the same clocked sensor, I need to generate timing for that. So how do I do that, right? So you use a different sensor, which is a simple inverter, which means the structure is a little different.
So every read and write, this replica will be get charged and discharged. So we have double the power energy.
Not double. Remember, there's only one replica for an array.
Okay.
An array might have 64, 128, 256 columns. And there,
Energy will be got double.
energy, there's only one replica bit line. Yes. And that bit line is, for example, it could be, whereas you have, say, 64 or 128 bits, right? Compared to that, you have one extra bit which is swinging full swing. Yes. So there is a overhead, definitely. There is a area overhead and power overhead, but that overhead is quite small compared to the savings you get because you are able to shut off the word lines and prevent the discharge of the bit lines.
The sizing of replica is different from the sizing of my other.
Replica cell will be exactly the same as your memory cell. It has to be the same.
But then
The sizing of the replica column.
one sense amplifier on that. So it has to be discharged faster.
That is why I am saying what you do is basically the bit line to which it is connected to is not, it doesn't go all the way. So what is done is basically you cut it off here. You have a small disconnect here. So this is a replica cell. It discharges its bit line, but the replica bit line is disconnected. You just open it up.
So I discharge only one line.
You discharge one line. Right? Yeah. Okay, so in the next class we'll look at decoders and how we can do fast decoding as well as this pipelining without using clocks inside the memory.